Okay, so today's theme is things you need to memorize for the IB, because there are some things, whether it's definitions or specific concepts, that you do want to either memorize or understand well enough that you don't have to kind of figure them out on the fly and things like that. And so this is going to be a mixture of SL and HL together. And so I'm going to try to stick with the red/orange for SL, and then the blue/violet for HL. So I'll try to make sure I keep those colors differentiated throughout this to make sure that we are, y'all know what to study, especially those of you that are in SL that are trying to prepare for the exam. And again, some of the stuff might be basic and some of it might be things that you're very familiar with, but I want to make sure that I'm very explicit that you need to know this. I don't want you to like be studying and go, oh, he never said I need to know this, so I'm not going to really look at this. And so we're going to talk about a lot of the things, starting from topic 1 all the way to topic 11 and 21. Terminology that you want to be able to use appropriately, definitions, all those things like that that you want to remember. Okay. Let's see. So topic 1, okay. A variety of things that you need to memorize in here, because topic 1 is kind of a comprehensive review of 10th grade chemistry. And so we're talking about moles, mole-to-mole ratios, limiting reactant, excess reagents, empirical formula, molecular formula, gas laws and solution chemistry, types of reactions, things like that. So all of this stuff, phase changes, that's all kind of bundled in this topic 1. So it's a very comprehensive review. And so that being said, there's certain terms that you definitely want to make sure that you are familiar with, because the IB explicitly says that you need to be able to understand these things. And so the first thing that I'm going to put on here is phase changes. Okay. And again, you're going to want to know all the major ones here. And so you've got your melting, your freezing, your vaporization, your condensation, excuse me, sublimation, and deposition. Okay, and so knowing the different phase changes there is really important, and also understanding which ones are endothermic and which ones are exothermic. Okay, so melting, of course, is from solid to liquid. Freezing is liquid to solid. Vaporization is liquid to gas, but again, you have differences in boiling and evaporation. Remember, evaporation only occurs on the surface and at any temperature, whereas boiling, that transformation occurs only specifically at the point where the vapor pressure of the gas is equivalent to the atmospheric pressure. And we'll talk about that a little more in equilibrium later on. Condensation is gas to liquid. Sublimation is solid to gas. Deposition is gas to solid. Okay. And in terms of exothermic and endothermic processes, we're talking about the system here. So you got to remember that we're talking about the system here, not what is being measured and things like that. And so when you deal with your endothermics, you're going to have those solids going to liquids or liquids going to gases. Those are endothermic processes because they're taking in heat. Freezing, condensation, and deposition are your exothermic, because the idea is that for the particles to get closer and closer together, their attractive forces have to increase. And if their attractive forces have to increase, the only way they are going to increase is if the particles slow down and that they are able to interact with each other more. And that's how those IMFs increase. And so differentiating between this endothermic versus exothermic concept is part of the nature of matter and how things change in here. And you also want to relate it to, and this is kind of in the chart as well, the idea of the heating curve we'll talk about this in the charts and tables as well, but you have your solid, liquid, and gas, and understanding what happens with temperature when you put heat into a substance. The idea is that when you're within one phase, all the energy you're putting in is increasing the speed of the particles. But each state of matter has a speed limit in which it can no longer go any faster in that form. And so when that limit is reached at these specific points here, then the particles have to break their intermolecular forces to allow them to spread out more and go even faster. And that's what happens with the phase change. So in the phase change where the temperature stays the same, all the energy is no longer going to particles moving faster. It's going into particles spreading out. So then they can, again, move faster again. And so that transition across here, you'll notice, has a constant temperature. It is completely flat because all the energy allows it then to go up in temperature. Questions about that? Okay. Within the mole, there are certain terms that we want to talk about in measurement terms. And so we talked about this yesterday in topic 12 or 2, but masses of individual atoms are relative to carbon 12. And so that this is where the idea of the atomic mass unit occurs, where it's 1/12 a carbon 12 atom, because a carbon 12 atom has 6 protons and 6 neutrons. So what scientists did was they said, okay, whatever the mass of that is, we're going to call that one mass unit. Even though protons or neutrons are slightly different, generalization is pretty effective here. And so this is why we call it the relative atomic mass, because it is relative to 1/12 a carbon 12 atom. And so that's why A, they're all whole numbers, and that's why B, you can use it to identify the number of subatomic particles because you're dealing with just one atom in that case. And so when you see like carbon 12 or carbon 14, 14 is the mass of that relative to carbon 12. So it has 2 additional particles in there, which happen to be neutrons in this case. And that's notated by AR. And then the relative formula or molecular mass is the same idea, but with a molecule, with an ionic/covalent molecule. So those values are in AMUs. Okay. Now, what we deal with here is the idea of molar mass, right? So a molar mass is in grams per mole to the -1 because that's 6.02 times 10 to the 23rd particles. So it turns out that 6.02 times 10 to the 23rd AMUs is equal to 1 gram. And that was intentional. When Avogadro calculated the value that he wanted to assign for Avogadro's number, that was intentional, such that the relative atomic mass in AMU would be the same as the molar mass in grams. So all of that was intentional in the derivation of that. Within this, unit as well, we talk about a couple of different things. Percent composition. Okay. Percent composition being usually the percent by mass of an element in a compound. And so when you're calculating this and things like that, you're looking at, like, for example, for CO2, the grams of C in the grams of CO2 times 100. Okay? And that is always consistent no matter how much sample of CO2 you have. And that's where we factored into the combustion empirical formula problem. Because when we do combustion, we're assuming that all the mass is conserved from reactant to product. So when you have two products and each product only contains the only source of that element, then you can extrapolate how much of that element was originally there based on the amount of products produced. And so that idea is really important for the application of the percent composition concept with the CO2 and the water and things like that. But then you also have empirical formula and the molecular formula, right? So again, definitions here. Is the simplest ratio of atoms in a molecule versus the molecular formula is the actual ratio of atoms in a molecule, meaning that's the may be able to be simplified to get the empirical formula. Okay, and so the molecular formula is always a multiple of the empirical formula by mass and by subscripts, but the empirical formula could be also considered a molecular formula. So if you multiply by a factor of 1, that still could be a molecular formula. It's not always true, but it can be. And with these kind of definitions, I think you're less and less likely just to have to recite them. It's more of applying them. If you looked at the multiple choice question that we did a few days ago, it wasn't a matter of defining empirical formula. They would find a way to ask the question, like, which of the following formulas has the largest mass for its empirical formula? And so you have to understand what empirical formula is, apply it, and then calculate to be able to kind of determine the result. And so I don't think they're going to say, what's the definition of empirical formula? You know, what they might say is, given this formula, state and explain whether or not it is an empirical formula. So you're applying the definition to give it context, but you're not like just kind of verbatim saying the definition. So in that case, you'd be like, yes, this is an empirical formula because the ratio of atoms is in its simplest ratio possible. Or no, this is not an empirical formula because the formula can be simplified into this formula, which would then be the simplest ratio of atoms. And so applying those concepts and making sure that you are able to speak about them is really important. And again, you can't assume that the IB grader knows what you're talking about. So you have to be very explicit about everything, and you have to establish definitions in your explanation. You have to establish these ideas. You can't just kind of say blanket statement. No, this is an empirical formula. You need to prove to the grader that you understand it. And that's what the mark scheme is looking for. It's like, does the student A understand what they're talking about? And B, are they applying it correctly to get full credit? So you do want to establish that in your explanations on the short answer, especially. Okay. Okay. Other terms that you are expected to know in this unit. Okay. Things like molar volume. Okay. So the volume a gas occupies at a specific temperature and pressure. Okay. And so 1 mole of gas, I should say, just to make sure that that's understood. And so for you at STP, it's 22.7 decimeters cubed at STP, but it can be a different molar volume at other temperatures. And so you may be expected to be able to calculate the molar volume of a gas at different temperatures and pressures. So understanding that is important. Another term, and these terms we don't use as much, and so you may not know exactly, you may not have exactly kind of memorized these definitions, so I'm kind of trying to bring them back. Like a standard solution, okay, is one of known okay, so one of known concentration is considered a standard solution. We usually use standard solutions to calibrate other solutions, like in a titration or in comparisons or calibration of pH probes and stuff like that. So like when we have our vernier pH probes, they can kind of deviate from the set values. And so you put them into standard solutions of known pH of 4, known pH of 7, known pH of 10 to calibrate them occasionally to make sure that the readings are still consistent for your experiments. Another one is an electrolyte, okay? I think we don't use this word as often, even though it is kind of self-explanatory. You want to make sure that what the issue with electrolyte is, and you want to make sure you're speaking clearly about it. An electrolyte is a solution that conducts electricity due to the presence of ions. Okay, and so this is different than the reason why metals conduct electricity, because of their delocalized electrons and things like that. And so it is important that we address that. So the solvent breaks down the substance into its respective ions, which allows it to conduct electricity. And you have strong, weak, and non-electrolytes. So a strong electrolyte kind of ties into the strong acids and strong bases and any salt that dissolves in water. Like NaCl dissolves completely into water, it's going to be a strong electrolyte. Insoluble solids don't form strong electrolytes, and like weak acids and weak bases form weak electrolytes. And then things like sugar and covalent molecules produce a non-electrolyte. So the idea of an electrolyte is something that you will see A, in acids and bases, B, in redox titrations, especially if you're talking about voltaic and electrolytic cells. And so there are connections to other topics about that. Questions about that? Let's see, what do I want to say here? Gas laws. Again, understanding the relationship between them, and then understanding kind of how that relates to your graphs and things like that. And so let's see, how do I want to do this? I think understanding this idea, the combined gas law, kind of helps you the most to understand this. And so seeing how these values relate to each other in this formula allows you to remember, okay, what is my relationship here? If temperature goes up, then pressure will also have to go up, because it has to be a ratio. And so the way I do it is I think about it this way, and then whatever's constant, I remove it. And so P1 over T1 equals P2 over T2. If T1 goes up to T2, then P1 will also have to increase to P2 to make these things equivalent to each other. Or rather, when T is constant, if P goes up, V has to go down to counteract that increase so that the values are the same because they're inversely related to each other. Okay, remember that term inverse relationship between pressure and volume, because that will help you also determine your graphs. Because when you have that P versus V graph, you want an inverse relationship as a generating curve. Whereas your volume or pressure, I guess I should write or just to avoid confusion, or pressure versus temperature in Kelvin is a direct relationship. It is a linear relationship between that. So if one doubles, the other one will double. Concentration. Okay. And so with concentration, we're talking essentially about the amount of substance in your solution. And so you've got things like molarity, which you know as moles per decimeter cubed. You have things like even density of a solution, which is grams per decimeter cubed. And so understand that there are different units of concentration, even parts per million, which we talk about in biological oxygen demand later on, is a unit of concentration. It's the distribution of a species amongst another species. And it should be it's applied to solutions because they're uniform in distribution, so their concentration is consistent throughout the entire sample. Molarity, don't forget you can use brackets to represent molarity. Actually, I'll write it like this, something like that. And so you can represent molar concentration with molarity. Questions? Topic 2, and I know we went a lot of this over this in some of your classes on Thursday and Friday, but I want to make it kind of consolidated here to talk about a few things that you do want to kind of memorize in this concept. And the idea of energy levels, sublevels, orbitals, and electron spin, where energy levels is n, which is 1, 2, 3, all the way to infinity. Sublevels are S, P, D, and F. Orbitals, there are 1, 3, 5, and 7. And if you want the number of orbitals in any energy level, it's n squared. So whatever energy level you are in, if you square that value, that's how many total orbital sublevels you should, total orbitals you should have based on the number of sublevels you have. And I think something that kind of is overlooked is the idea that every energy level gains a sublevel. And so you have to understand that 1 has S, 2 has S and P, 3 has SP and D, 4 has SP, D, F, etc. And so every energy level gains an additional sublevel, and that's why the number of orbitals increases overall. And that way, the number of total electrons that can be held increases as well. So number of total electrons is 2n squared because every orbital can only hold 2 electrons max. Okay. And they do, I don't think they direct, let me see. Oh, shoot. Because I've seen this before, understanding the shape of an S orbital versus a P orbital in here. So an S orbital is a sphere, is a spherical shape with its center being the nucleus. Whereas a P orbital comes in three varieties, px, py, and pz. And those subscripts denote which axes that p orbital is aligned with. And so a px is aligned with the x-axis. The py is aligned with the y-axis. And the pz is aligned with the z-axis. So make sure you're aware of that, because that could be a very simple short answer question saying, illustrate what the shape of a pz orbital looks like. And not only do you have to know what a p orbital looks like, kind of a dumbbell, but also that the z means that it is on the z-axis. Some students may just draw a p orbital like they do in px and say that's correct, and that would be wrong because it has to be on the z-axis to be recognized as the pz atomic orbital. Okay. Also, don't forget about emission spectrums and continuous spectrums and line spectrums. And so your line spectrum is a specific set of frequencies of light displayed. So this is what happens when each element gives off its own light. There's only fixed lines that you see. Now, it varies on the number of lines you see, but it will be specific distinct lines that you can see in there. Whereas a continuous spectrum is all frequencies of light. And with that line spectrum here, you'll want to think of a hydrogen emission spectrum, and I'm not going to go into detail here, but you need to know the following things: that when it jumps down to n equals 1, that releases UV light. And when it jumps down to energy level 2, that's visible. And when it jumps down to 3, that's infrared, which makes sense because UV is higher energy than visible, which is higher energy than infrared. And so understanding what level an electron must return to release a photon that releases that frequency of light is important. And that could be a short answer question very easily. Just given an emission spectrum that's blank lines and say, illustrate using an arrow the a transition that would generate a visible light photon. And so you would have to go anywhere above 2, going down to 2 in the arrow, and you have to point the arrow down to 2 because it's the energy release that releases that photon. Electron configuration exceptions. Okay, so while electron configuration 98% of the time is very consistent by reading the periodic table, there are 2 that are not natural. And that is copper, which is AR4S1 3D10, and CR, which is AR4S1 3D5, which is different than the way you would normally write it if you were following the convention for it. Because for CR, you'd write as 4S2 3D4, and CU, you'd write as 4S2 3D9. But that electron, because the energy state of 3D is so close to 4S, the reduction of the repulsion by filling up or half filling the D sublevel outweighs the benefit of having a full S, which then still would be a half filled S, which is still very stable. And so knowing these exceptions really important, because like I told some classes, CU plus is a favorite electron configuration the IB likes to ask about, because you not only have to A, know what CU's normal configuration is supposed to be, B, understand that you lose electrons from the outermost shell, which in this case is 4s. And so that way, there are a lot of different wrong answers that can occur based on a lack of knowledge here. But for CU, it is AR 3D10. Because just because you don't fill those electrons in last, the outermost shell is always the easiest one to escape from. Even if it's lower energy state overall than 3D, it is just located physically further out. So it's going to be the first one to escape because it's closest to leaving the atom. So make sure you kind of remember that when you're thinking about which electron you're losing in electron configuration. You also need to know the three principles or three laws of electron configuration or orbital diagram. Off-bow principle. Ground state of an atom requires electrons to fill in lowest energy sublevel available. Okay, so the ground state is the way you would fill in the electrons from 1s all the way up into wherever you're going for the element. When there's an electron in a higher sublevel or energy level than it should be, that's called an excited state. So know that term as well. So an excited atom means, all it means is it hasn't lost or gained an electron. It just means one of the electrons or more than one are in a higher state than it should be. And eventually excited states return back to their ground state. And that emission of light is what you see. So I'll leave this here for a second. But we're moving on to topic 3 and 13 now. Some of the stuff in topic 12 is going to relate to charts and graphs and equations, and that will be covered in the next 2 Saturdays. But this is just kind of more of a, oh, I'm sorry, I didn't finish the 3 different rules. Hund's rule, apologies, got ahead of myself here. Hund's rule states that in a sublevel with multiple orbitals, each orbital receives 1 electron before any get 2. So if you have a p sublevel with 3 orbitals, each orbital gets 1 electron before any of them double up. That way you minimize the repulsion, because anytime an electron's in its own orbital, it's going to minimize its repulsion. And you don't want to increase that repulsion until you absolutely have to, which is when you double up the electrons in those sublevels. And that's why they point in opposite directions. Which leads us to our last rule, which is the Pauli exclusion principle, okay, which states that orbitals can only hold a max of 2 electrons with opposite spin. Okay, this is why you see the arrows pointing up and down like this on your paper when you draw them. That's really important to notate, that they're spinning in opposite directions to minimize repulsion. And so it does state in the syllabus tracker that I'm following that you do need to know these names specifically: off-bow, Hund's, and Pauli exclusion. Maybe for a multiple choice question, maybe for an explanation in a short answer. Maybe they give you an electron, an orbital diagram, and state what's wrong with it. And so you'd have to cite the different rules that are being broken when it's wrong. Questions so far? Topic 3 is kind of the periodic trends. And so I'm going to assume that you know the group number and the period number concepts like by now. So I'm not going to state them, but the terms that you definitely want to know about describing different groups are your alkali metals, your alkaline earth metals, your halogens, oops, I made the common state, your noble gases, your section that is your transition metals, and your lanthanides and actinides series. Now, the lanthanide actinide series, that's your F block. So those are the elements that are at the bottom of the periodic table in their own 2 separate rows. And they're called lanthanide and actinide because those are the elements that start those series. Lanthanum and actinium are the first elements that begin that row of elements that we consider the F block. So know those terms and know the location on the periodic table of where those are as well. Within this, we also have the periodic trends, and there's a lot of memorization in this. A, knowing what the trend is, and B, knowing how to apply it. And right now, I'm just going to focus on kind of definitions, and the application we've kind of gone over several times. But the definitions that you tend to need to know are things like ionization energy, okay? The energy change required to remove one electron from an atom. I guess this is first ionization energy from an atom in its gaseous state. Because once you lose that first electron, now it's an ion. So then no longer are you losing from an atom anymore. So it's second and third and fourth ionization energies are just losing from the species after it's already lost one. Okay. So key idea here is, again, removing that electron. And that is an endothermic process. And so you see a generic one like this reaction to represent it. You see that connection between the the atom and its cation here of losing an electron, and this is going to be a positive delta H. You're gonna have to put energy into the system to give an electron enough energy that it can escape the attraction of the nucleus. Electron affinity is the energy change when an atom gains an electron in its gaseous state. So kind of the opposite of ionization energy, where you're actually gaining an electron to form an anion. But when you look at your period and your data booklet, these aren't always negative. They don't always release energy when you add an electron. So be careful about that and don't assume it's always exothermic or endothermic, respectively. And so the value of the electron affinity varies from species to species. Sometimes it's positive, sometimes it's negative. Electronegativity is the attraction of a positive nucleus for a shared pair of electrons. Okay, and this scale is relative. Whereas ionization energy and electron affinity are measured in kilojoules per mole, as they should be with enthalpy, electronegativity is more of a comparison, a relative scale. And so it goes from 0.7 to 4.0 and doesn't really have a unit. It's just kind of a scale derived from its interaction with each other. And so francium is your 0.7 and fluorine is your 4.0, because fluorine has a combination of characteristics that make it the best at electronegativity: a small radius and a large effective nuclear charge, because it has the most protons in that period other than noble gas, which doesn't bond. So it has the greatest attraction for its electrons. So that's the idea of electronegativity. Questions so far? One set of terms that I don't think you talk about a lot is metallic versus non-metallic behavior. And you don't need to get really into this, but when you're talking about what increases metallic behavior and what increases non-metallic behavior, with metallic behavior, you want to think about the ability to oxidize, because metals want to lose electrons, which makes them more reactive. And so when you look at metallic behavior, you ask yourself, okay, which of these metals is it the easiest to lose an electron from? And when you answer that question, you'll know which one has the most metallic behavior, because it's the easiest one to lose electrons and act as a metal. Whereas a non-metallic is ability to reduce or gain an electron. Okay. And so a species that wants to gain an electron wants to be A, smaller, B, have more of a nuclear charge, because that way you can pull the electrons closer in. Whereas a metallic atom wants to lose an electron, so you want bigger and bigger and bigger, more shielding, weak nuclear charge, which makes it a lot easier for the metal to react with whatever it's coming into contact with. Okay. This next table is kind of talking about a bunch of different properties of the period 3 oxides. And so the IB likes to talk about the period 3 oxides here, and this is still SL. So period 3 oxides are any oxide formed from a period 3 element. And so that's from sodium oxide, magnesium oxide, aluminum oxide, silicon dioxide, tetraphosphorus dicoxide, sulfur dioxide, sulfur trioxide. And that's as far as you're really going to go here. I mean, you could write like Cl2O or something like that, but that one won't really get into as much detail. And what you need to memorize here are how the characteristics change as you go across the periodic table. And so you need to know that these two are basic oxides, because when they react with water, they form hydroxides. For example, Na2O plus water yields NaOH, 2NaOH. MgO plus water forms MgOH2, which is already balanced. So that one is, those are strongly basic. Al2O3 is amphoteric, meaning it can act as a Lewis acid or Lewis base by gaining or losing electrons. And then the rest of these are acidic oxides, meaning that when they dissolve in water, they form acids. Now, you don't need to know every single reaction here. You need to know two of them, P4O10 and the SO2 or SO3 reaction. The SiO2 is kind of a tricky one because it doesn't act as an acid in water, but if you react it with a base, it will act as an acid. So like you don't need to know a reaction for that, but you do need to know that P4O10 plus water forms H3PO4, and that's 6. I'm sorry, that is 4, 6, and 1. And you know that you need to know that SO2 plus H2O is H2SO3, and SO3 plus H2O is H2SO4. So those reactions you do need to memorize. Now, there are shortcuts you can think about, like with the metal oxides, you just have to know that makes hydroxide. You don't have to memorize each reaction specifically. You just have to know it makes the hydroxide. And the acidic ones, you have to know that they make an acid. And the rule of thumb is the acid generally has the same oxidation number for that element as the original did. And so like SO3, S is +6, and then H2SO4, it is also +6. So if you're not sure if it's the right acid, make sure the oxidation number stays the same from the reaction of the product. If it doesn't, then you have the wrong acid in your reaction here. So that's a good point to think about. Within this, you kind of have your ionic compounds, your giant network covalent, and then your covalent molecules, or simple covalent molecules. I think some people use that term. Simple, not being that they're not complicated, but simple meaning that each individual molecule can stand on its own. Whereas diamond or silicon dioxide, they can't. They are in an entire network and they can't exist without being part of that network. So when I say simple covalent, I mean the simple characteristic of it being independent. Okay. And along with that comes conductivity as well. And so with this, conductive as a liquid, aqueous, and gas. And fairly non-conductive for your silicon oxide and moving on to the right. Okay. So yeah, memorizing equations is starting to kind of show up here in this aspect. Other reactions you need to know, okay? Alkali metals with water. So an alkali metal with water forms the metal hydroxide and H2 gas, because you're going to have excess H2 gas there because you're making hydroxides, and every water is a hydroxide with an additional H. And so there's extra H that is turned into a gas that's then released. And so the metal with the water forms metal hydroxide and H2, but the metal oxide does not, because it has the right ratio of oxygen to hydrogen to make everything into hydroxide. So there's no wasted hydrogen in those reactions. Okay. You also need to know like alkali with halogen. So like Na plus F2 yields NaF because they synthesize together. And you also need to know that halogens can replace other halogens. Same way with activity series, F has to be greater than Cl, which is greater than Br, which is greater than I. And so if you see something like F2 plus NaCl, you will get NaF plus Cl2. Because the F being more non-metallic in character tends to lose electrons and forces chlorine to gain those electrons and revert back to Cl2. And another way to look at this is ionically, where it's just this. Because the Na doesn't actually do anything, it's just a spectator ion. It's just there to bring the species, the ion species, into the solution, but it never reacts itself. Okay. The first higher level thing, this is the first kind of topic of higher level where there's things that you need to memorize in here. Okay. One, the characteristics of transition metals. It is a list, and the IB generally finds one list to kind of incorporate into each kind of paper too. And so this list of characteristics, okay, one, variable oxidation states, okay. They form complex ions. They form colored compounds. They display catalytic and magnetic properties. Okay, so do not confuse this with why transition metals do this versus what are the characteristics of it. So characteristics or properties of transition elements mean that they have variable oxidation states, they form complex ions, they have colored compounds, and display catalytic and magnetic properties. When you talk about split d sublevel and partially filled d orbitals, that is no longer the characteristic you can observe. That is why they have variable oxidation states. That's why they form colored complex ions. That's why they have colored compounds as well. So don't write partially filled d sublevel unless you're trying to explain why they give off color, or why zinc is not considered a transition element because it has a full d sublevel. And someone said something very insightful in one of the classes yesterday. It was that, like, copper ion, Cu plus 1 is a full d sublevel. So you won't see colored compounds with Cu plus 1, but you will see it with Cu2 plus, because Cu2 plus has a 3d9, which means it's partially filled. So most of those colored compounds you see for copper are 2 plus, like copper sulfate and copper nitrate, copper chloride. All those different colored solutions are generally Cu2 plus ions being produced. Okay. We will put in here why as well. It's not explicitly stated, but it is something that they like to ask about a lot. Why do they form colored compounds and things like that? Let me clarify that. So why do they form colored compounds? Okay, so structurally it is the split d sublevel having partially filled d sublevel as well. So when the ligands attract to the metal ion, they split the d sublevel, which then splits the electrons, which then allow electrons absorb light to jump up to higher d sublevel state. And then light not absorbed, which is your complementary color, is seen. So that Roy G. Biv helps us figure out what the complementary colors are by looking at colors that are opposite of each other. And this only works with the split D sublevel because the split D sublevel splits just enough that the energy transition is visible light, which is why they create colored compounds like that. And don't forget that the color is dependent on three things. One, the identity of the metal ion. Two, the oxidation number. And three, the identity of the ligand. So those are the three factors that affect what color you see in a colored compound, because all three of those factors affect how much this d sublevel splits, which means what kind of energy does the electron need to have to jump up to the higher split d sublevel. Questions so far? We are going to go on to topic 4 now, which is bonding, which does have quite a bit of memorization that you need to be familiar with to be able to do this. Okay. You have to know, one, definitions of bonding. Okay. So like we said in class, you have to know the idea that an ionic bond is an electrostatic attraction between oppositely charged ions. You could say positive and negative. You say cations and anions. Both of those are acceptable alternatives for that. For a metallic bond, you have to know it's an electrostatic attraction between positively charged ions, also known as cations, and a delocalized sea of electrons. Okay, so every type of bond is just an electrostatic attraction between two different things. Ionic, it's oppositely charged ions. For metallic, it's delocalized electrons. You don't have to write C, I guess it's kind of redundant. But, and then positively charged cations, because all the metals gave up their valence electrons to form this delocalized area volume of electrons, which holds the metallic bonding all together. And then we have covalent, which is an electrostatic attraction between a positive nucleus and shared electrons. Notice I didn't say cation. Cation is a very different thing. A cation is formed when you lose or gain electrons. A covalent bond doesn't do that. A covalent bond shares electrons. And the thing that holds them together is those electrons being shared between the two nuclei. Both nuclei are pulling in equal opposite directions to try to attract those electrons. And that's what keeps that bond existing. Questions so far? Okay. In here, also, you need to know the terms volatility, electrical conductivity, and solubility. Okay. So these three kind of definitions are not necessarily concrete definitions, but you have to be able to kind of apply them. So again, a volatility is the rate at which a species evaporates. Okay, so the higher volatility means the higher the rate at which it evaporates. So acetone has a very high volatility because if you pour acetone on a table, it's going to evaporate fairly quickly. Whereas water has a very low volatility because it has strong hydrogen bonds, strong hydrogen bonding IMFs, which keep the molecules close together. Okay. Electrical conductivity, ability of electrons to move through the species. And for ionic compounds, you're either going to melt them down so that the ions can move freely, or you're going to dissolve it in water, and then that allows the ions to move freely as well. And so both cases allow free moving ions, which allows electrical conductivity. Solubility is the ability to distribute evenly throughout a solvent. So are the particles able to break down and be distributed evenly throughout the solvent, or does it clump up and solidify and fall to the bottom? When it clumps up and solidifies and falls to the bottom, that's considered insoluble. Like you might have an insoluble precipitate, or you might have a soluble, well, you wouldn't have a soluble precipitate, you just have a soluble solution if it weren't a precipitate. So know those definitions because you may need to discuss them in other types of questions. Okay. Polyatomic ions you need to memorize. Okay. And the IB is very explicit about this list. It is a list of 10 ions that they hold you accountable for. Okay. And I like to organize them by charge here. So there's a 1+ charge group, there's a 1-, a 2-, and a 3- charged polyatomic ion list. 1 is ammonium, which is NH4+. Next is hydroxide, which is OH-. And then nitrate, which is NO3-1. Cyanide, which is CN-. Ethanoate, which is CH3COO-. Hydrogen carbonate is HCO3-1. Then we have carbonate, which is CO3-2. We have sulfate, which is SO4 2-. Oops. We have dichromate, which is CR2O7 2-. 4, 5, 6, 7, 8, 9. And then we have phosphate. PO4, 3 minus. So these polyatomics, you're held accountable for their formulas and charges and names. Other ones that they give you, they will probably give you enough information to deduce what it is. But these 10, they are holding you accountable for whenever you use them, whether it's acid base, whether it's redox titration, whether it's organic chemistry, all of these species you do need to know. Okay. Um, let's see. Sorry about that. Other things we need to know here, kind of memorizing wise. Resonance structures. Remember, resonance structures have delocalized electrons. Okay. And so with these, you have certain structures where a double bond is able to fluctuate between different regions. And so the electrons are what we call delocalized. And so while the IB says you don't need to know these, like there are other ones than the ones they list, I'm going to talk about the ones they list and a couple more. And those are the main ones that show up. Okay. The first one is benzene. Okay. So benzene has 3 double bonds that alternate around in a ring to form that structure. You also have ozone, which has the alternating double bond between the central oxygen. And knowing how to draw these resonance structures is important as well. Also, we have carbonate. Carbonate's the one where you have the 3 possible structures of carbonate. And you do need to write the charge for those structures as well. And so it rotates around. And you want brackets and a charge to show that resonance. And the other one I think they really like a lot is ethanoate. Because ethanoic acid can't resonate because there's a hydrogen bond to the oxygen, but ethanoate because it's lost that hydrogen, now the CO bonds are identical. So what will happen is the double bond will alternate between those 2 regions of CO. And that's why the bond length in carbonate, in ethanoate is shorter than a double bond because they're sharing equivalent electrons. And so it's almost kind of like 1.5 bonds, whereas carbonate's like 1 1/3 bonds for the equivalent. Also, don't forget, you need to memorize the allotropes of carbon. It's been a while since you've probably seen that, but you need to know the allotropic carbon of diamond, graphite, graphene, and Buckminster-Fuller. Buckminster-Fullerene. So each of those structures, and you need to know SiO2 as well. These are kind of ones you have to memorize because there are specific structures in here. And so I do have a diagram here that I'll put up for those, so we don't have to draw them out because I'm not very good when it's drawing those structures out. Okay. So with these structures, you have to understand the kind of shape they make. And kind of what shapes they have. And so graphite is 3 carbons bonded to each carbon, forming hexagonal sheets that are held together by LDFs. Graphene is one of those sheets in graphite. A diamond is a tetrahedral where the carbons bonded to 4 of the carbons. Fullerene, it's bonded to 3 other carbons and it has 12 pentagons and 20 hexagons in its shape. So understanding that will help you kind of understand the characteristics of this, and graphite being a fairly conductive species because that extra electron moves between sheets of graphite, so it's delocalized, and so therefore it is able to conduct electricity. Remember SiO2, even though it looks like CO2 because it's in the same group as CO2, it is not the same as CO2. And it forms a giant network covalent solid like a diamond, essentially, but instead of just carbons, it's Si and O. Let me show you what that looks like here. I have it here somewhere. This. So notice with SiO2, it's a giant network covalent. It's not like CO2 where it's 2 double bonds to oxygen. It is I think fullerene is okay. I don't know. I don't think buckyball is an appropriate technical term for it. So I would stick to fullerene or Buckminster-Fullerene as your terminology there. Okay, no problem. Okay. But again, with SiO2, notice that it is a network covalent where Si is actually bonded to 4 oxygens in a tetrahedral shape. But the reason why it's SiO2 is because each oxygen is bonding to 2 silicons. So the ratio of the silicons to oxygen is 1 to 2. Okay. Do we need to memorize the pentagons and hexagons in fullerene? I think so, because if they ask you to describe the shape of a fullerene, that you either memorize that it's 12 pentagons and 20 hexagons in a kind of spherical shape, or you memorize the name truncated icosahedron, which I think I'm going to go with pentagons and hexagons, because even if you say soccer ball, they don't accept that. You would have to say a soccer ball shape with 12 pentagons and hexagons and 20 hexagons in it. So I would know those specific numbers for that. Okay. And again, like some students have been doing already, feel free to put questions in chat, and I will keep an eye on them and respond to them as well. Okay. Speaking of shapes that you have to memorize, that is where this comes into play as well. We're going to kind of create a big chart of this with electronic geometries. Headlighting the top part. As so. Oops, let me. So the shapes that you need to memorize. And like I've said before, I find instead of memorizing all 15 shapes for HL or all 6 shapes for SL, I think drawing the electronic geometries and then manipulating those afterwards will help you minimize what you have to memorize. And again, that's the goal of this thing, because even now, as I'm going through the stuff you need to memorize in this whole class, I'm finding that's a lot more than I thought it was going to be. I thought we're going to finish by with some time to spare, but I don't know now because we're only halfway through it. And so it may be a little bit easier later on, but it's a little less memorization in future topics, but still there's content in there. So our 5 shapes for HL, our 3 shapes for SL that are electronic geometries are linear, trigonal planar, tetrahedral, trigonal bipyramidal. And I think if you say bipyramidal, it's acceptable because this is the only bipyramidal shape, and octahedral. Okay. Now, electronic geometries, again, are shapes that occur when you don't differentiate between lone pairs and bonding pairs. They're all the same. Now, if you have no lone pairs and they're all bonding pairs, then these can also be your molecular geometries. So don't think that these are only electronic geometries. They can also be molecular if you have no lone pairs on center. But when you start having lone pairs on center is where you get different molecular geometries than your electronic geometries. Okay. And this is why I draw it this way, to kind of help you visualize what's happening in these structures. Because if you write the electronic geometries and you just start removing lines in specific manner, then you can figure out all the other shapes without having to memorize every single term and every single descriptive shape. And so with these, the way I draw them, I always first take the line pointing up first. It helps me visualize what's left. And so you can see here that when I take this line off, what I'm left with is bent. When I take this line off, what I'm left with is trigonal pyramidal. And then when I take off another line, this is bent. Because it's not 90 degrees from each other, they are actually more oriented in 3D space. They don't cancel each other out. In higher level, they do though. So like here you see saw, here you see T-shaped, here you see linear, because in this linear, the 3 electron pairs that are replaced by lone pairs are all vectors that cancel each other out. And so the repulsions cancel out. So the remaining 2 bonds are able to be exactly flat from each other to minimize repulsion. Whereas octahedral, you have square pyramidal, you have square planar, you have T-shaped, and you have linear. Questions so far? So I'm not going to go too much in hybridization and stuff like that. We'll kind of apply that a little bit later, because that's not necessarily something you memorize. You're looking at the number of regions around the atom, and that helps you with hybridization. But these shapes you do kind of have to memorize. And you can label all of these are molecular. It's only the first top row of 5 that are electronic geometries. Questions so far? Okay. Another thing you need to memorize are your IMFs of simple covalent molecules. So that's your London dispersion forces, your dipole-dipole, and your hydrogen bonding. So be able to identify which structures have which of those IMFs, because you may have to use those because those affect physical properties. And just like in your mock exam, you had to identify the IMFs before you get full credit to explain which one was stronger and why that would affect the volatility of the species there. So make sure that you remember those LDFs, dipole-dipole, and hydrogen bonding concepts. Okay. For a higher level, I just wanted to talk about a couple of things here. And we'll take about a 5 or 10 minute break after this because it's been a lot of stuff. Is sigma and pi bonding. Okay. And so knowing the definitions of these things does kind of help you understand why one is weaker than the other and things like that. And so sigma bond is an end-to-end overlap of orbitals between the two nuclei. And so it creates a density of electrons in between the two nuclei that are bonding together. A pi bond is a parallel overlap of p orbitals, creating electron density above and below the plane. So this is higher level. So I think this illustration will probably show you the best about what this will look like here. This CO2 hybridization, I think, kind of helps you see sigma and pi bonding. So you can imagine where the letters the C and O are the nuclei, and the sigma bond is between the two nuclei. So it's a stronger bond than a pi bond. A pi bond is just a parallel overlap, and so the orbitals don't have to cover a lot more distance to create attraction, so it's always going to be weaker. That's why a pi bond is weaker, and that's why the bond enthalpies don't increase by a factor of 2 and 3 when you get a double and triple bond, because pi bonds are weaker than sigma bonds. One last thing for higher level. Okay. Okay. CFCs and NOxes. Okay. Now, with this, you need to know the mechanism of the catalysis of this. And so we have the initiation, the propagation, and the termination of this. And so initiation, you have that UV light and you create that Cl free radical. Okay. And that Cl free radical reacts with ozone to form a new free radical. And then that free radical combines with another O3 to form the Cl free radical and two O2s again. Some books will say this as ClO dot plus O dot yields Cl dot plus O2, and that's okay as well. I think both of them are acceptable here because the idea is that ozone, when it breaks up, does form oxygen gas and O free radicals. And so that characteristic does happen as well. And so you can kind of see that in this kind of process here. And again, the termination step, I don't think the termination step is that important. It's more about these propagation steps that we really care about here. Okay. So it doesn't look like we really talk about the termination that much. So it's mainly that propagation that we care about here. With NOxes, the idea is that the NO2s and NOs break up and form NO free radical, and that reacts with ozone to form NO2 plus O2. And then the NO2 reacts with O free radical to form more NO plus O2. So this is not so much a propagation, this is more acting as a catalyst. So notice that NO dot is being used up and then produced again here to speed up the destruction of the ozone. Okay, so both of these actually look fairly similar. And I think if you just memorized, this reaction, let me change the highlighting here. I think if you memorize this reaction and this reaction, you could literally replace the Cl free radical with NO free radical and still get the same equation. And so that would be the kind of the main idea here. So that's what you want to focus on here, is that it's breaking it down. So know those reactions, that those catalysis reactions that help explain why ozone breaks down. Okay. Let's take a 5 to 7 minute break here. I'm going to pause the recording. Okay, so topic 5 is enthalpy and thermodynamics, essentially. And so what the things you need to know here, I'm not going to go into all the calculations and stuff like that, but I'm going to talk about kind of more definitions. So delta HF, which is standard enthalpy of formation. We will go into the calculations of like Hess's law and like using enthalpy of formation, enthalpy of combustion next week when we spend the whole Saturday session on calculations. And so we will see that again next week. But right now, I just want to establish definitions so that you can kind of discuss them. Standard enthalpy of formation, energy change when 1 mole of substance is formed from elements in their standard state. formed from elements in their standard state at standard conditions. So if you're looking at a reaction, like for example, something like NaCl's formation, it would be Na solid plus 1/2 Cl2 gas. So again, the key phrases here are standard state elements, standard conditions, and 1 mole of substance. So the reaction always produces 1 mole, even if it requires fractional coefficients for the species. So things like C2H4 would be 2 carbon solid plus 2 H2 gas to form that. Okay. Which is different than standard enthalpy of combustion. Oops. Which is the energy change when 1 mole of substance combusts with oxygen. So now the species in question, if you want the molar enthalpy, if you want the standard enthalpy of combustion of something like C2H4, it would be react O2 to form CO2 gas plus H2O, I guess at standard conditions too as well. That's what that symbol up there means. Okay. And so 2, 2, 3 in this case. So that's the standard enthalpy of combustion, or the molar enthalpy of combustion as well, because it's per 1 mole. Bond enthalpy, okay. Energy required to break 1 mole of bonds in the gaseous state. Okay. So this would look like something like this. Now, bond enthalpy is less accurate because A, there's average bond enthalpies, and B, some substances aren't naturally in gaseous state. For example, Br2. So the value that it takes to break that bond in gaseous state is kind of muddled by this phase change and things like that. And so keep in mind, bond enthalpy is probably the least accurate of the enthalpy calculations because of those factors here. Okay. For a higher level, in topic 15, you've got other ones. You've got lattice enthalpy, which is the energy to convert 1 mole of solid ionic lattice into gaseous ions. Okay. And so looking at this, it would look something like this. And this is going to be the endothermic version, because all the values in your data booklet are positive, meaning that it is the endothermic version of converting solids to gases. But in the Born-Haber cycle, it's the opposite. So you need to flip that sign around when you're trying to solve for it. And so keep that in mind with this as well. Okay. Also for higher level, you have to know enthalpy of hydration. Oops. Of hydration, which is essentially, well, let's just do gas going to aqueous. So the energy it takes, the energy change that happens when a gaseous ion becomes dissolved in water, almost always exothermic. And on top of that, enthalpy of solution, where your solid becomes aqueous. Let me rewrite that there. It's hard to see. Okay. So the energy it takes for that to dissolve into aqueous ions is the enthalpy of solution. And that can vary. It can be exothermic or endothermic based on the lattice enthalpy and the hydration, because enthalpy of solution is a combination of lattice enthalpy and hydration. This being the hydrations, this being lattice enthalpy. And again, for here, you'd have to 2x it because the hydration is just for 1 mole of Cl minus. So you'd have to double it here to solve for the enthalpy of solution of that salt. Also for higher level, you're going to want to keep in mind delta H minus T delta S for delta G. And yes, you get this equation in your short answer, but there are possible multiple choice questions about this. And this is more in multiple choice, it's more kind of qualitative, meaning that at what conditions does it become spontaneous? And so the sign of delta H and the sign of delta S help you answer that question. So knowing this equation allows you to go, okay, it's always spontaneous, or it's never spontaneous, or it's only spontaneous at high temperatures, or only spontaneous at low temperatures. So applying those signs of delta H and delta S by identifying the process will help you be able to predict what the sign of delta G will be. But I'm not going to write the entire chart of it out right now, because again, minimize what you have to memorize here. And remember, spontaneity is delta G is less than or equal to 0. That is a concept you definitely want to remember. Back to SL in topic 6, which is kinetics or reaction rate. Okay. Collision theory is one concept you definitely need to memorize, because for a reaction to occur, 2 particles have to collide with the correct orientation and the correct energy, which we call the activation energy. Okay, it has to meet the minimum activation energy required for the reaction to occur. Okay, and activation energy is, like we said, minimum energy required for a reaction to occur. And collision theory, these 2 bullet points are what you explain when you talk about why factors affect the rate of reaction. So why do certain factors like concentration increases the frequency of collisions, so more particles will have the correct orientation. Temperature increases the energy of the particles, so therefore more of them will collide with the correct energy, but they also collide more often, which means the frequency of collisions also increases with that. And so applying those concepts is really, really important. The idea of a catalyst, like you saw on the mock exam, addresses two things, this definition. So catalyst lowers activation energy of the reaction by providing an alternative pathway. It seems that the Marx scheme was very emphatic that you had to say alternative pathway in here as well. So it does it by providing an alternative pathway. That's why the reaction diagram looks like this for a catalyst, as opposed to this as an uncatalyzed reaction, because it's providing alternative steps that make it easier for the reaction to occur without by accomplishing the same task to reach the same conclusion. Higher level. Okay. With this, I think the only thing you're really going to want to memorize is understanding the graphs of concentration versus time and rate versus concentration. And so that's where you have the 0 order, first order, and second order reactions, where when you measure concentration versus time for each of these, it looks like this for the reaction. But then you have to remember that if you graph rate versus concentration, then it'll look like this. I think the rate versus concentration graphs are easy because they correlate to the rate law, right? Rate equals K, rate is equal to K times A to the first, and then rate equals K times A to the second. So these graphs here below this line are pretty intuitive because they're just mathematical functions. I think understanding how these graphs and the slope of those graphs are the rate helps you, are important to memorize, to be able to identify what type of reaction, what rate of, what order of reaction is occurring. Also for higher level, you have your calculation for activation energy. And so you want to know here that your graph is natural log of K versus 1 over T, and mind the units on that x-axis. That 1 over T might be times 10 to the negative 3 or times 10 to the 3 instead of just the number that's written on there. And frequency factor, which we write as A here, also known as the Arrhenius constant, factors in the frequency of collisions with the correct orientation. And so that term frequency factor shows up a bunch because if they do a question about this paper too, they'll ask you, what does A mean? What does A represent? So A represents the likelihood of a collision being correct orientation, because at infinite temperatures, which is pretty much the y-intercept, it doesn't matter what the energies are because they all have the right amount of energy to react. It's just a matter of how often are they colliding with the correct orientation to react in itself. You take a temperature out of those as a factor. Topic 7, equilibrium. Okay, first of all, you have to know the definition. When a closed system has the forward and reverse rates equal. Okay, so when the reaction rates of the forward and reverse reaction are equal in a closed system, that is equilibrium. And we mathematically represent equilibrium as K or Kc. And remember, we do it as products over reactants raised to their coefficients. And we also have to address Q there. Okay, so Q identifies at what state the reaction needs to shift to reach equilibrium. It may already be at equilibrium, or it may have to shift left or right to reach equilibrium. So that Q value is solved for the same way as K, but we compare Q to K to figure out how that affects it. Okay. Okay. Topic 8 and 18, acids and bases. Okay. Being a little bit more kind of particular about things that I cover now. I think I covered way too much stuff in the first kind of half, but that was last year. So probably any exposure to the topics from last year is going to be beneficial. And so going a little bit deeper is okay. Acid base. You need to know the Bronsted-Lowry definition of acids and bases, and that involves a proton or an H+, donor and acceptor for acid base, respectively. Remember, we use the term amphiprotic in terms of Bronsted-Lowry, which can act as an acid or a base in terms of Bronsted-Lowry. Okay. Knowing what a conjugate acid base pair is, identifying that. Okay. The acid reactions, this is something else that you do need to memorize as well, is the fact that acids react with a lot of different substances. They can react with metals to form metal salts and hydrogen gas. They can react with metal oxides to form the salt plus water. I'm not balancing these right now because I don't think that's the main important idea of it. They can react with metal hydroxides to also form salt and water. They can react with carbonates or hydrogen carbonates to form salt, water, and carbon dioxide. Okay. And you can write this as a hydrogen carbonate as well to form a similar compound here. It just balances differently. So knowing these reactions will A, help you be able to predict products, and B, helps you differentiate between acids, because whenever you're trying to differentiate between a strong and weak acid, the rate at which the reaction occurs with these species is what helps you, is one way to help you identify those ideas. Know your strong acids. For our purposes, it's HCl, HNO3, and H2SO4. Those are our strong acids. Everything else that's an acid is weak. And every group 1 or group 2 hydroxide is strong. But I want to mention a weak base that you always need to remember about, which is ammonia. That will be probably the only weak base that they'll probably address in the entire test here. So be familiar with that. Okay. pH is a negative log of H plus, and H plus concentration is 10 to the negative pH. Again, math calculations we'll talk about next Saturday. Okay. Methods to differentiate between equimolar acids of different strengths. So I say equimolar, so therefore I know the concentration is the same, so I can use the concept of strong and weak acids to differentiate them. And I also say different strengths because one will be strong and one will be weak. And so the way you can do it, and I'm going to ignore pH or titration because usually they rule that out as an option. The main ones you have are conductivity, and reaction rate with a carbonate or a metal, because either one will produce a gas which you can visibly observe to see, okay, is it making it more vigorously or is it making it more slowly? And conductivity is the same way. Is it higher conductivity or lower conductivity, which relates to the extent of ionization for these species? Those are the two main techniques that I would use to differentiate. Acid deposition. Okay, remember, rain is already slightly acidic naturally occurring because CO2 dissolves in it, so it's 5.6. It's the problem when you get further down, which is what caused the issues. And so you have things like nitrogen compounds and sulfur compounds, NOxes and SOxes, that produce these different acids. So they react with water to produce these acids, which lower the pH even more than usual. And like I said before, I think the main one you want to know is this one, the NO2 one, because the NO2 one is not very intuitive. The SO2 and SO3 ones are pretty intuitive because you just combine them together. They're just synthesis. But NO2, you have to know it actually breaks up into two different acids here, HNO2 and HNO3. And that's the one that IB usually tests on. So if I'm going to memorize one of these reactions, it's going to be that one. Okay. Don't forget sources. Oh, sorry, not purple. sources of these nitrogen compounds come from decaying plant matter and the internal combustion engine, whereas SOXs come from volcanic eruptions and coal burning. And within this, in pre-combustion, we just remove the sulfur. And in post-combustion, we use chemical scrubbers, such as CaO, to react with the SO2 to form CaSO3. For higher level, there's really two major things that you need to kind of memorize. The Lewis acid and base definition, okay, where it has to do with electron pair acceptor for an acid and electron pair donor for a base. Okay, so know those definitions, be able to identify and understand that Lewis acid base definition is more encompassing than the Bronsted-Lowry. So every Bronsted-Lowry acid base is a Lewis acid base, but not every Lewis acid base is a Bronsted-Lowry acid base. Okay, second thing is buffers, right? A buffer essentially contains a weak conjugate acid base pair. To reduce the pH change in a solution when a small amount of acid or base is added. So if you're trying to identify buffers, look for a conjugate acid base pair that's weak, or the ability to make one when you combine those two things together. And it resists the pH change. I guess resist is probably a better word than reduce, to be honest with you. I knew there was an R word. Resist the pH change in a solution when a small amount of acid or base is added. Topic 9 and 19. Okay. Oxidation and reduction definitions. There's three of them, and you need to be aware of all three of them, right? The first one is loss of electrons and gain of electrons. The second one is gain oxygen or lose oxygen, which is usually related to, sorry, not gain, lose hydrogens and gain hydrogens. And the last one is increase oxidation number and decrease oxidation number. So make sure that you know these three definitions because you will be tasked with applying those definitions in different contexts, whether it's a reaction, whether it's a descriptive thing, or whether it's an experiment. Understanding those differences is really important because they will be specific about which definition they want you to apply in your answer. And if you don't apply the right one, you won't get full credit. And don't forget, oxidation states are +2, not 2+. And you will be docked for not writing in the correct convention. 2+ is charge, +2 is oxidation number. Okay. Oxidizing agent, reducing agent. Oxidizing agent is being reduced, and the reducing agent is being oxidized. That's why it's being facilitating the opposite. Biological oxygen demand, the Winkler method. A couple things you need to memorize. 1 mole O2 is 4 moles of SO2, S2O3 2-. This is known as thiosulfate, in case you see that word or that formula for this, thiosulfate. And also you need to know that you need to go from moles per decimeter cubed to milligrams per decimeter cubed to get the O2 concentration. So you have to convert moles all the way to milligrams because this is parts per million. Voltaic cell and electrolytic cell, understanding the diagrams for this and kind of understanding the main ideas. And so I'm not going to label everything here. Like I said, I'm trying to tell you about things you need to memorize. And so I would say the things you need to memorize are electron flows from anode to cathode. And pay attention to the diagram and see which way the electron flow is designated, because that's important that you establish which one's the anode, which one's the cathode. I know you get into the habit of assuming the anode's on the left, but on the IB exam, they could very well have the anode on the right if you're not paying close attention. You don't want to miss that, okay? The anode is negatively charged. The cathode is positively charged. The anode is oxidation. The cathode is reduction. Oops, I'm just trying to make this smaller so it didn't take some more space. Ellie doesn't like that. The electrolytic cell, and we'll talk about this a little more in higher level in the details you need to memorize. But again, electrons still flow from anode to cathode. So pay close attention to that. The anode here is positive and the cathode here is negative, but it still undergoes the same reactions as the voltaic does. And so there is a similarity there between that. It's just the charge is different because in an electrolytic cell, you have to create a non-spontaneous reaction. And the only way you're going to attract the negative ions in your solution or molten salts to get to the anode to give up its electrons is if you make it positively charged, because this is not a natural spontaneous process. So you have to apply electricity to allow this reaction to occur. Questions on this? Don't forget salt bridge as well, but I just want you to know the major ideas about this, because labeling a cell may show up. It was showed up on the mock exam. It showed on other multiple exams in the past. If you've taken some practice paper twos, they do like giving you a blank diagram and asking you to label stuff and charge and things like that. For higher level, things you need to memorize: the standard hydrogen electrode. You need to know the characteristics of it, meaning 1 mole decimeter cubed of H+ ions, 100 kPa, and 298 Kelvin H2 gas, and platinum electrodes, or inert electrodes, either way. So know those characteristics, because those characteristics lead us to the standard hydrogen electrode potential. Not standard hydrogen, standard electrode potential. I was just looking up there, which is our E0, okay? Because it is defined as the potential of the reduction half reaction relative to the SHE. So whenever you hook up these half reactions, you always make the SHE the oxidation, and you make the other half reaction the reduction. And if you get a negative value, then that means that other thing is a better oxidizer. If you get a positive value, that means the other thing's a better reducer, and then the electrons are flowing the right way. So do know that the electrode potential is based on so know that definition here. And along this, well, I guess with those electrode potentials, you need to think about electrolysis of aqueous solutions. And that is quite a bit of application as well. And try to figure out how much I want to say of this. And so we have NaCl aqueous, okay? And you need to know that water's competing here. And so you might have the reduction of water, and you might have the oxidation of water. And NaCl, again, I'm going to kind of focus on the memorization aspect and not go too much into theory about this, but the idea is that in a dilute solution, you make H2 and O2. H2 at the cathode, O2 at the anode. Because the Cl is in such low concentration, it doesn't react. But in a concentrated solution, still the Na doesn't reduce, so you'll still get H2 at the cathode, but you will get Cl2 at the anode, because in high concentrations, Cl is more attracted to the anode than water is, and so it's able to oxidize, even though it's slightly worse at oxidizing. The copper sulfate one depends on if you have inert electrodes or copper electrodes. If it's inert, then the anode is going to be O2, because water is going to always oxidize in the presence of that because there's no metal to oxidize. But the cathode will be Cu based on the cell potentials. In the copper, the anode will oxidize into Cu2 plus, and the cathode will produce Cu. So there's no net change in that one. I'm not going to go over all the observations. That's something that you can kind of infer based on what you see as your products for those reactions. You can talk about color change. You can talk about precipitates being produced and stuff like that. But right now I'm looking at multiple choice questions where they might just ask you, state what's being produced on the anode and what's on the cathode for these. And remember, in electrolytic cells, the anode is positive and the cathode is negative. And last thing for HL here, for topic 9 at least, current, duration, and charge of metal ion. This all has to do with electroplating. So those are the 3 factors that affect how much you can electroplate. Okay. Organic chemistry is quite a long one, and we will let's do organic chemistry and topic 21 and 11 in class. I think we've kind of looked at a lot of stuff today. And so this will give us some stuff to go over in class next week. And so on Monday and Tuesday, and maybe Wednesday and Thursday, we'll go over things you need to memorize for organic and NMR, HNMR, IR, mass spec, and analytical chemistry and stuff like that. So we'll kind of go over that throughout the week as well. So I think it's a good starting point because organic chemistry is so memorization heavy. I don't want to rush through it in these next 30 minutes. So I'll space it out over the next couple class periods. Okay. So what we've gone through so far is topic 1 and 1, 2, and 12, all the way to 9 and 19. And then in class, we'll do 10 and 20 and 11, kind of 11 and 21.